Hey everyone, it's Mr. Montgomery again. Today we're going into lesson number 2 on thermal energy. And today we're really going to be focusing on the transfer of heat and how we can make that happen. Because you might be thinking, well, it just happens. When I want things to get hot, I can go turn on a stove and make it hot. Yeah, but there's something specific you always got to do at a stove, right? You can't just magically have the heat transfer from the stove to a pot across the room. Right? They sometimes they have to make contact. Other times they have to just be close up to each other, or maybe there's a fluid involved, and then that changes the how the heat's transferred as well. So that's really what we're going to be focusing on today. And after today's lesson, you're going to be able to tell me all the different methods that heat can be transferred. That is my goal for you guys. All right, but let's do some review off of the previous lesson before we go diving in. So which choice to the right would have the most thermal energy? Remember what we had discussed about that? So here are your choices. Is it a bathtub full of water, a boiling hot cup of coffee, or a pond that is 35 degrees? Did you pick your answer? It would be the pond, because it's all about the greatest number of particles. And if you guys remember the video that we watched during our Ed puzzle, they also compared a cup of coffee to an iceberg. And then they were able to show us that an iceberg had greater thermal energy because the cup of coffee was not strong enough to make it change its state, right? Because you pour that cup of coffee on that iceberg and it will solidify, it'll freeze. And the coffee, the heat from the coffee doesn't melt the entire iceberg away. Okay, here's our next review question. Which temperature scale has no negative values? Is it Kelvin, centigrade, Fahrenheit, or Gatorade? Pick an answer. I hope you did. And I really, really hope you didn't pick Gatorade, because, come on, that's a drink. I mean, it's tasty, don't get me wrong, especially the frost flavors, but that's not what we're looking for. And if we want the temperature scale that has no negative values, we're going to go to Kelvin. Because remember, the freezing point is 272 degrees, I believe, and then the boiling was 372. You still have that 100-degree difference, just like with centigrade. Okay, now before we go into all the different methods that we can transfer heat, I want you to take a guess. I want you to brainstorm, take a guess. How many different ways do you think we're going to be able to transfer heat throughout this lesson? All right, take a little guess. Okay, I hope you did. And the number is 3. We're going to learn about these 3 specific ways to transfer heat. First, we have conduction, which is shown in this picture as the hot mug touching the countertop, just like I mentioned in the previous video, right? You put a hot cup of coffee on the table, right? Leave it there for a few minutes, pick it up, you touch that counter or the table, and the table's nice and warm from that transfer of heat. It's all that thermal energy. So we're also going to be talking about something called convection, which gets a little fuzzy for some people, and that's okay. The main thing you're going to just need to remember about convection is that it has to do with fluids. And remember, a fluid can either be a liquid or a gas. And then lastly, we have radiation. And with radiation, look at the top of this mug. You see these heat wavy lines kind of like emitting outwards from the top, right? That is radiation. You can feel the heat from a distance from any object or material without actually having to touch it or have any direct contact, which is pretty cool. And radiation can be done in a few different ways, and we'll go into that throughout the lesson. So, in all of the heat transfer methods that we are going to discuss today, do not forget the one super duper duper important rule about thermal energy. Heat, when heat is being transferred, when there's thermal energy and you're transferring heat, it will only flow from areas of high temperature to areas of low temperature. It will never go from areas of cold temperature to hot. It doesn't work that way. So we're going to start with conduction. And this picture actually shows a little example of conduction. I'm going to explain that in a quick second. So when we discuss conduction, this is the transfer of heat through two stationary objects. And guys, remember, the word stationary means it is not moving. And we're not going to go super technical and say, well, you just said in the last video that all these atoms have all these moving particles. I know. There is kinetic energy involved. I get that. But relative to us, meaning based on our perception of these two objects, like the spoon and the soup, they're not moving off the table, are they? It's not growing, it's not shrinking. There is no movement based on our perspective relative to us. So we have these two stationary objects that are in direct contact with one another, right? You have this spoon that was originally pretty cold, and you left it in this bowl of hot soup. And we've all been there where you have something really, you have like a spoon or fork that's been placed into some hot food, and what happens when you put that spoon or fork into your mouth? You burn your mouth, right? You burn your tongue or your lips. You feel that pain, you feel all that heat being transferred from that fork or spoon now to your mouth, and you're in pain. That's all through conduction. So this also means that heat is transferred from one particle to another without movement of matter. So that means that the soup particles don't have to go into the spoon in order to transfer heat. They are not moving around. They're not. They might have been at one point, but now they're not. Okay? And the reason I even said at one point that they were is because of the next method that we are going to discuss after the example. Okay? So for the example of conduction, if you have an electric stove at home, so there's two different kinds of electric stoves. There's one that it kind of might look like a metal coil, kind of poking out. That's an electric stove. It's an older model. Still works fine. And the newer models are called glass top conduction stoves. These are still electric based. So there is a transfer of energy from electricity into the stove, and it generates heat or thermal energy to have heat radiate off the top, and then you can put any pot or pan on top of that glass conductive stove and use that to heat up your food and anything you're cooking. That is conduction. Because if you were to take this same frying pan and while you're cooking, you just lift off the stove, it's going to start cooling down. It no longer has that heat source being transferred straight into that frying pan until you put it back down, and then you would see, you would even hear the sizzling start all over again once you finally have it or allow it to make contact with that stovetop. So if you really want to dive in deep for a quick second, so first with the stove, the particles are starting to move fast on this electric stovetop because you have all that kinetic energy build up. And then when a pot or frying pan is placed on top of the stove, the heat is transferred to it just by being placed on top because it has direct contact. That is the premise, the main point, so to speak, about conduction. So let's think really quick about something before we jump into our next slide. Have you ever watched a pot of boiling water? What happens when this water's boiling? So you see some visual things happening. You might even smell some things. You might even might have it look like something's leaving the pot, right? So I just want to think about that for a quick second before we go on. Think about everything you've ever noticed in that pot of boiling water. Are there bubbles? Do they move? Does the water look different? Does it feel different? Would you touch it? Why not? All these things are super important because the next method of transferring heat is going to be convection. And convection is specific to fluids. And like I've mentioned many, many times before, a fluid has, we could say, two different states, right? We could say that a liquid is a fluid, but also a gas is a fluid as well. So this phenomena you observed while watching a pot of boiling water, this is called convection. Convection is when heat is transferred within a fluid, liquid or gas, and that fluid continuously circulates to colder areas. So if you've ever watched that pot of boiling water, I know you have, because we've all done it. We've all been memorized when we were younger. And what happens is this bottom part, where all the heat is being transferred directly to, is the hottest part. Right? All this water down here is the hottest, and all the water up top is the coolest. I know if we were to touch it, it would still feel burning, burning hot, and it would hurt us really bad, which is why we don't touch boiling water. But relative to the water at the bottom, the water at the top is much cooler. So what happens is, as the bubbles start to form at the bottom, the super hot water at the bottom of the pot expands. And as we all know, as material heats up and expands, it likes to rise up. Same thing with if you ever take a shower or bath, you see the steam rising up. Or think of a hot air balloon. You fill that balloon full of hot air, it rises. Same thing with a super hot fluid. It will want to rise to the top. But once it hits that top, it starts to instantly cool down a little bit. And when a liquid cools down, it starts to become more dense. And I know that sounds weird, but it does. So it stops expanding and starts contracting a little bit. Think about your muscles when you try to flex your bicep. You're contracting your muscle, making it all condense into one spot. And that naturally happens when things get cold. So you can think of any liquid that you freeze, it's going to condense. And when that happens and it cools down, it starts to drop back down because it is more dense than the water at the bottom. And then once it's the bottom, it starts to expand again because it's heating up, and then it wants to rise back up to the top again, and it keeps circulating in this motion all the entire time. And so when heat is transferred to the water, that fluid becomes less dense. This is everything I was just saying, but I'm going to just restate it just in case it didn't make sense the first time. And it rises to the top since it is expanding and becoming less dense, and rises to the top. The top part of the pot is slightly cooler, making the water at the top slightly more dense. This creates a continuous flow where the hottest water is continuously rising and the cooler water is continuously dropping down to the bottom and sinking. This also, like I mentioned, guys, this also goes for gases, because gases are also fluids. If you've ever heard of a convection oven before, that is an oven that circulates the hot air within to make sure that the food cooks properly and evenly. That is, if you've ever watched Food Network, that is the gold standard of oven for anyone that is really into baking cookies or cakes and stuff like that. Okay, and our last method of transferring heat is radiation. Radiation is a transfer of thermal energy through electromagnetic waves. This method does not require matter in order to transfer thermal energy. And the reason we say that is, look at the sun. The sun is radiating thermal energy 24/7. So 24 hours a day, 7 days a week, 365 days a year. It doesn't stop. It just feels like it does because we're facing the other direction, right? But then this also goes into other variations of that, which I really want to make sure you guys have a good grip on. So some other examples could be a light bulb. Well, you might be thinking that makes sense right away because the sun radiates light and a light bulb does the same thing using electricity, so that makes sense. But the ones that kind of catch people off guard are any hot liquid that is allowing it to escape, radiate upwards. That could be one example. also a match. This is technically electromagnetic radiation as well. It does give us light to see. Therefore, it is also an example of transferring heat through radiation. And it's also emitting that heat, allowing it to escape in all directions, going upward and every other direction possible. And then same thing with the burner on a gas stove, right? It is creating flames. Flames are electromagnetic energy. It is allowing to transfer heat without having direct contact onto those flames. You could even test this out if you really wanted to, if mom and dad were completely okay with it. Or if you've ever been to a campfire, right? Go to a campfire, you put some marshmallows high above the fire so it doesn't burn on you. But what happens is you're transferring all that heat and thermal energy to the marshmallows, and they start to slowly brown because they're cooking, and then they get gooey and hot and warm, and then you make s'mores out of them. Whew. I feel like I'm talking a lot. But that's kind of what we need to do. Well, what I need to do. Because I need to make sure you guys get this. So, now that we've gone through all the different ways of transferring heat, let's put it into practice. Which picture would you say shows conduction? Are you going to say it's this first picture, the middle picture, or the last one? Because remember, conduction, you must have full contact between the two objects or surfaces. And I'm hoping you guys were saying this one. I'm going to put a CD for conduction, because that spoon is in the hot liquid, and it has direct contact to that liquid. So then the liquid is transferring heat all the way through the spoon. Next, let's try to figure out the convection part. So we have two left. Is it going to be the open flame or the boiling pot of water? And I'm really hoping you're pointing to the boiling pot of water. Because if you remember those pictures, it has that circulation going through here where all the water at the bottom is heating and expanding and rising to the top. And then once it's at the top, it gets cooler and condenses and then falls back down. And it's this whole cycle that goes over and over and over. Which means that the last picture is radiation. All right, cool. I'm hoping I'm not going too fast. If at any point it feels going too fast, just rewind the video a bit, okay? Or rewatch it as many times as you need. Maybe a day later, because you're really having some trouble with those 3 examples that we went over with. Play the video again tomorrow when you have some time, right? If there is time. And then when it gets to this part, pause it before you see the answers, and then try to see if you can get them all correct. Okay, now we have to go into conductors and insulators. Now we've talked about this with electrical energy, and just like electrical energy, there are conductors and insulators for heat as well. They do, and they mean the same thing. A conductor with electricity means that it allows electricity to flow through very easily. A conductor with heat means that it's allowing to transfer thermal energy very easily, or transfer heat. And then with an insulator, of course, is the opposite. Just like with electricity, an insulator will not allow a good flow of electrical currents. And with thermal energy, it will not allow a transfer of heat to go through very well at all. So when discussing thermal energy, a conductor is any material that transfers heat well, like I just mentioned. And metals like steel and copper are great thermal conductors. These are great examples. When we talk about transferring heat, any metal is a great conductor. Aluminum, gold, copper, iron, steel. Any metal you think of will be a fantastic conductor, because they will heat up pretty quick, and then they will retain that heat as well. And as for insulators, of course, like I just mentioned, an insulator is something that does not, or a material that does not transfer heat well at all. And some really great examples are going to be wood, because if you heat up wood enough, it stops being an insulator and just combusts and will start to burn. It doesn't really hold heat and allow it to transfer through it very well at all. Another great example is going to be plastic. Plastic does not conduct heat well at all, which is why the handles to many pots and pans are made of plastic. And lastly, styrofoam is a fantastic insulator. If you've ever been to a hospital and they've brought you like a cup full of ice chips, it's always a styrofoam cup because it keeps them cold for a very long time. Or if you guys remember a couple years ago, back when Dunkin' Donuts had styrofoam cups for their coffee and hot chocolate, it kept that coffee and hot chocolate hot for a super long time. It felt like it took forever for it to cool down so you could finally drink it and enjoy it. Because it's a great insulator. But unfortunately, styrofoam is very bad for the environment, and it takes a super long time for it to biodegrade. Okay, and before we finish up today, guys, here is our last check-in for today. Now I know you can't circle. It says circle at the top, but I know you can't. So you can just point to your screen at the correct answers. So I want you to point to the pictures that show great conductors for transferring heat. We have wood logs, copper wires, plastic spoons, and aluminum cans. So make sure you point to your answers real quick. And the first one is, well, actually, let's start at this end. Are wood logs a good conductor? No. These are not a good conductor at all. They will actually block the transfer of thermal energy, and then when it gets up to a certain temperature, it will just start to burn. How about copper wires? Will that transfer heat very well? Yes, it will. Copper is a great conductor. How about a plastic spoon? No, plastic spoons, they're not good conductors either. And last, you have an aluminum can. We're going to pretend that it's not full of Dr. Pepper and that I drank it already. So what would you say? Yes, no, maybe? I'm hoping you're saying yes. It is a great conductor, and that is one object that you could definitely use to help transfer heat. And that's it for lesson number 2, guys. So I hope that this helped clear up anything there's or anything you're possibly confused on. If you're still a little confused about something, please let me know. I will do my very best to make sure it is not confusing for you. Or if you're not in my class and you're watching this video, please make sure you go ask your teacher to help clarify anything you might be still a little fuzzy on, and they'll help you out. But as always, guys, I'll see you next time, and have a great day.